I am S. Divakar, ME Structural Engineering, and my project title is Experimental and Numerical Analysis of Battened Cold Formed Columns Subjected to Compression. My project guide is Ms. Jimmy Marin Isaac, Assistant Professor, Department of Civil Engineering, Well-Tech, High-Tech, Dr. Rangarajan, Dr. Saguntala Engineering College. This is outline of presentation. Generally, cold formed steel is differ from the hot rolled steel members. It is manufacturing by rolling or pressing the cold formed steel sheets at room temperature. It may be lead to more economic design than the hot rolled steel members as a result of the superior strength to weight ratio and ease of construction. It is commonly used as wall studs and cord member of roof trusses. It can be used efficiently where the hot rolled members are not efficient. These are the applications of CFS members. First one is CFS expressed wall system and next one is CFS purlin. This is cold formed steel columns. Advantages of CFS members: lightweight, high strength and stiffness, ease of prefabrication and mass production, fast and easy erection and installation, no formwork needed, economy in transportation and handling, recyclable material. Generally, cold formed steel structural members are subjected to different buckling modes, that is local buckling, distortional buckling, flexural buckling and torsional buckling. Objective of my project is to study the strength and behavior of cold formed steel columns subjected to compression. Need for the present investigation. Finite element analysis program Abacus is proposed as an alternative to predict the actual behavior. The section was selected based on the North American specifications for the design of cold formed steel structural members 2007 edition. In that, the geometric limitations are available for single section only. Based on the single section, box type of build-up section was selected. This is the geometric limitations of lipped channel sections as per North American specification 2007. Experimental study. I have selected box type of build-up sections for experimental and also parameter study with different cross sections. This is cross section details of the specimen, and the dimensions were derived from the limitations of North American specification, and the spacing is provided based on the moment of inertia about major axis is equal to the moment of inertia of minor axis. Length of the specimens provided based on the slenderness ratio by using the formula lambda equal to L effective by R minimum, and number of the battens have formulated based on the maximum spacing. This is test setup and this is failure mode. Development of finite element model. The elements are generated by cross section and extruding along its length. The material properties like Young's modulus, shear stress, Poisson's ratio and thickness were defined. The model was measured and the end conditions were created. This slide shows the development of part and the development of meshing and merging of battens and end conditions. First one is local buckling obtained from the buckling analysis, and next one is failure mode of the column obtained from the nonlinear analysis. Results and discussion. In the present study, experimental analysis for the specimens with various slenderness ratio and number of battens were done. Also, numerical analysis was done for the same specimens by using finite element software Abacus 6.1. From the results obtained, the following comparisons shall be made for the columns. This slide shows comparison of loads of finite element analysis and experimental analysis. Graph was plotted between load and axial shortening. It contains experimental and also film analysis results. This is the comparison of experimental and finite element analysis results. Parametric study. For parametric study, I have selected two different cross sections. First one is 90 cross section and next one is 150 cross section. For 90 cross section, I have analyzed the slenderness ratio range from 20 to 120 and the batten width is 53.08 mm and R minimum and spacing of the cards are derived from using the custom software. Length was derived by using the slenderness ratio from the formula lambda equal to L effective by R minimum, and the number of battens was derived from by using the maximum spacings. The graph was plotted between load versus axial shortening for the slenderness ratio range 20 to 120. The maximum loads are given. Mainly it shows when the slenderness ratio increases, then the load carrying capacity will be decreased. And same procedure have done for 150 cross section also. This is the graph of 150 cross section. These are all the deformed shapes from Abacus software. Conclusion. Totally 44 axial loaded built-up battened columns were numerically studied and 10 columns were experimentally tested. The following conclusions on the axial compressive strength of the built-up battened columns are drawn within the limit of the present investigation. The development of finite element models are in reasonable agreement with the test results available in literature. Therefore, Abacus program can be used to simulate battened columns. Based on the parametric results, a simple design expressions can be proposed to predict the ultimate strength with further study with experiments to validate. The ultimate strength of the member decreases with increase of overall slenderness ratio irrespective of section geometry. For slenderness ratio between 70 to 120, the predominant failure mode is distortional buckling. That's all. These are all the references of my project. Thank you.